So now we're actually going to have a panel on scientific funding for deep learning. And we're very fortunate to have senior representatives from multiple funding agencies joining us for this. So in particular, our panel is going to have Robert Bonneau, the Associate Director for Data Analytics and Software in the Office of the Secretary of Defense, Hava Siegelmann, Program Manager at DARPA, Henry Kautz, Division Director of Information and Intelligence Systems at the NSA, Richard Reekin, the U.S. Air Force Office of Scientific Research, and our moderator is Juan Meza, Professor of Applied Mathematics and Dean of the School of Natural Sciences, UC Merced. So as I mentioned, after this panel, we'll be having a reception, and we hope you'll take that opportunity to both speak with some of the panelists on some of the topics raised and our counterpoint speakers. Thank you.
All right, well, welcome everybody, and thank you for sticking around for the panel. We've had a great set of talks on science in deep learning, and this panel will address the issues of scientific funding for deep learning. And we have already, I think, been introduced of the four speakers we have here today. In the interest of time, I'm just going to let them say what they're going to say. And unless there's a preferred order, why don't we start off with Henry and then work my way back over here. And if we have enough time, we'll try to take a question or two. But we do know that there's a reception right between now and us. So.
Okay, and are there any slides, or should I just imagine them?
Yes.
What?
Slides, okay.
I sent in my slides.
All right. Oh, wait. I see something.
Oh,
There you
okay,
go.
great. Wonderful.
Okay.
Okay, so I'm Henry Kautz from National Science Foundation. In the directorate that is Sports Computer Science, and my own division is Information and Intelligence Systems. And what we call our core programs, every directorate has core programs, core research in AI, data science, and human-computer interaction. We often find many projects, particularly around deep learning, might have all three of those aspects. There's also core work appearing in some of the other areas, such as math, so I won't try to be exhaustive. I decided just to limit myself to programs that have upcoming deadlines. So in this core here, we have September and October 2019 coming up. But about half of all the money at NSF actually is in cross-cutting programs. So given this audience, you probably have quite a few people who receive funding from collaborative research in computational neuroscience, a very interesting program, multidisciplinary, multi-agency, and international, as well as related programs such as the BRAIN, B-R-A-I-N. But AI works its way into many cross-cutting programs, such as the National Robotics Initiative, which focuses on ubiquitous collaborative robotics, smart and connected health, and again we see deep learning, as well as other machine learning applications for healthcare coming up, and smart and connected communities, where we look at AI technology in natural and built environments. So that's just a sample, probably about, I don't know, maybe 2/3 of the ongoing program supporting deep learning in general in AI and machine learning. I'd like to mention a couple of new programs you may not be familiar with that some may be interested in. One is the Future of Work at the Human Technology Frontier, an interdisciplinary program bringing together technology with the social and behavioral sciences. So the impact of essentially AI-powered automation on work, as well as new opportunities for AI-assisted work, and particularly when we're looking at opportunities for human augmentation. There's many people have written about how truck drivers will eventually be eliminated by autonomous trucks, and so they should all become programmers. Or I have heard other speakers say they should just all become unemployed. A more likely future is probably we look at new jobs such as remote truck supervisor. So again, a deadline that's coming up soon. A really interesting major new effort we have called Harnessing the Data Revolution, again across the entire directorates, the foundations of data science, including machine learning, as well as data intensive science and engineering. So there are several solicitations out for this right now. One is Institute frameworks. So these are $2 million over 2 years to help launch an institute, and these institute may be a domain. So it could be, big data in neuroscience. That could be one, or it could be, big data in agriculture. To be followed by a down select and competitive renewals. The deadline for that is in May 2019. We also had another solicitation. I did put it up here because it's already passed. This would be ideas labs for institutes, and so you'll have to wait till next January if you want to get involved in those. But there is one coming up very, very soon. One of the major programs that funds really foundational work in data science, and particularly that brings together mathematicians with machine learning peoples, has been called tripods. And there's going to be a new generation of tripods, transdisciplinary research and principles of data science, bringing together mathematicians, statisticians, and machine learning people. And I've just put in red there that the letters of intent are due in just a couple weeks. You then have a month or two to write the proposal. And finally, just a word on AI strategies, because in addition to giving up money, we try to think about, well, how to do that thoughtfully. So NSF has helped fund the Computing Community Consortium, which is a branch of the Computing Research Association, to generate a 20-year roadmap for AI. And this is this report's the result of 3 workshops and broad input from the research community, and that report will be coming out in April. We also have an interagency, the AI Interagency Working Group, which involves essentially every agency that funds anything in computer science, a national AI strategic plan. It's an update to the one that came out in 2016 under the Obama administration. And that also will be coming out again in April. But since I've seen drafts of both of these and helping to create the latter, I can say they both call for many things in common, in particular the need for larger sustained academic research support, something like national AI or national machine learning centers, and in particular support for open AI infrastructure. As in Anthony Traubel's talk, he mentioned this cycle of research that goes through Google. Right now, if you want really high quality infrastructure machine learning, you're dependent upon Google or Facebook. And that's great, they're doing it, but we also think that there should be programs that could support equally high quality AI and machine learning infrastructure from the academic community. Thank you.
Great. Thanks, Henry.
Is there another?
Yeah.
Oh, you don't decide, okay.
Yes, slides, okay. All right.
Okay, I think this mic's on, so I'm just going to sit here. I'm Bob Bonneau, and I work for the Office of the Secretary of Defense, and our office has lots of different science programs that go on, and I have the privilege of working with people like Hava and Doug to execute those programs. But one of the things we've been thinking about a lot lately are the advances in deep learning and a lot of the things this workshop's addressing. And it's great to see everybody has come out to kind of participate in, where all this is going. I think some really important trends, which I've been talking about a lot with people, and it turns out this is not an entirely new discussion, are really digging into the mathematics of what makes the deep learning mechanism really work, and characterizing that in terms of when it works and when it doesn't. To give you an example of why that's important, increasingly we consume the products of deep learning just in the course of what we do daily. So on your on all of your personal devices, you're reaping the benefits of natural language processing and translation and all of that. When we consume that sort of thing, particularly in the Defense Department, we have to be sure that we can trust what's coming out of those algorithms. And that's a function of two things. It's a function of the data that goes into them, and it's a function of the algorithms themselves. And so mathematically, if you start to look at the sort of underpinnings of what's needed to really understand that at the scale we're dealing with now, which is considerable, having the ability to mathematically characterize the internals of what that high-dimensional state space looks like in terms of all the weights and things that you're dealing with, and really robust metrics for risk in terms of what those loss functions look like if you don't put the right class of data into that algorithm are really critical. And so one of the things I'm encouraging folks to really think about in how they sort of construct their programs and work with the academic community is how how we consider those things. And it's interesting because in some cases, particularly the medical community and some of the self-driving car community, there are some very sort of specific efforts to really characterize risk and safety and all those properties of deep learning and how it how it actually plays out in reality. But in the broader class of algorithms, sometimes those risk metrics are very different for places like the Department of Defense than they are for sort of people who would use them in other contexts, commercial or otherwise. So, getting that right, really having robust metrics, understanding the sort of internal state machine of these things, and having more advanced mathematics and statistics to characterize them is critical. And so, at least personally, I'm going to try to, encourage the funding to go in that direction so that we can really, enable a deeper understanding of what's going on. No pun intended. But beyond that, really, foster the scientific community to really go in this direction. And last but not least, and I know I work with NSF a lot too, so it's great to hang out with you guys. Really making that multidisciplinary connection to enable that. That's really important, and you can see that reflected in some of the solicitations we just heard about. So that's it. Thanks.
So much. Our next speaker is Dr. Siegelmann. We can get our slides up, please.
Okay. So we seem to be now in some type of a crossroad of computation. So for the last 70 years, we pretty much assumed the Turing computation, and in the sense that when we think about computation, we think about following a program, and the Turing computation is very much open to its input, and when you have new input, it drives new output. So the same thing that you have for the last 70 years, you have in your own calculator in the 1980s expert systems and in the current deep learning. So you can think about current AI or current machine learning or deep learning, that you have a training set and you learn, and then you become a real expert in object recognition or in pattern recognition. And after this training is done, the AI is frozen. So after programming and training, there is nothing more that happens, and AI really computes what it was taught to, what it was given, what it was planned, what it was trained to do. But there is another type of computation that we know of, and we know of it from biology. And this is the super Turing computation. So when we think about computation in biology, we think about something that is really more than what we have in the Turing computation. So in Turing computation, the input causes changes to the programs itself, and then also to the output. So this change of the program itself is what we call learning. Now, in biological system, we have both the Turing and the super Turing computation, but it is this property of changing the program of the learning that makes the biological system able to learn on the go and be ready to stand in situations that never been before. So as we go to the super Turing AI type, we now can start talking about this type of situation that we haven't been ready for, and we didn't just learn from what we had in advance, but over the lifetime of the system, we managed to continue learning and training so that we'll not be stuck with something else that we're not prepared for. This is very useful, and this is the basics for the lifelong learning machine, which is a DARPA program, my DARPA program. So in lifelong learning machine, we try very much to have this realization, ideas from biological, mathematical, and computer science ideas, to have realization to the super Turing idea. So we try to have now this kind of new generation of systems that they can learn while they execute. So they become more expert during their lifetime as they apply more experience, and they can apply this experience to new situation. So let's look at this graph. The X is the time, the Y is performance, and for example, we can think perhaps about a self-driving car. I just update this picture for Amnon in his honor, but I put Tesla, just to be sure. Okay, so what we do is during the training, there is more and more information that is being presented in the training set, and there is a great performance. And then as the training is done, the system stays the same. And it cannot be better, so if it does mistake on something, it will continue making exactly the same mistake on the same thing, because it doesn't have this capability to open up and relearn. If it goes to some situation that it was not ready for at all in the training set, the performance will go down, and there will be no way to learn from experience to realize that we're in a new situation and to start doing something else. So in order to have a different type of AI that will be able to be better for critical operations, we would like to have these capabilities that when we see that things are not going that well, we'll open up again, and the system will become better and better, it will improve, so that after some time it will be so much better after the end of the training cycle. And this is really the heart of the lifelong learning program. So now in the lifelong learning, we're already 11 months into the program, and we also already have some very interesting results. This is just to say it's a very large program. We have 17 regular performers, but 30 total performers, which is the largest in DARPA's history. And talking about, I want to just to mention the notion of scientific collaboration. So when I started with the original definition and analysis of super Turing, I put together some ideas from mathematics and computer science and biology, but when we come to lifelong learning, this is really crucial. So we have within this program a group of biologists and neuroscientists, and we're still open for more, which we come to them with the one question. It's not like take the money and go and do whatever you want, but we have particular question. How is it possible to do continual learning in biology? So continual learning is just that you have more input and you can do better and better without necessarily forgetting what you had before, which is the basic for any animal learning, but was not the case at all in AI, perhaps until very recently. So we asked them very particular question, how we can do context-modulated computation. So for context-modulated computation, for example, if I want to emphasize that I'm very happy with something for a toddler, it can be, yes, 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 do it again, good job. And you know, if you want to encourage perhaps a teenager and you don't want to use exactly the same word, maybe you'll be as expressive as saying. But the general idea is that when you want to encourage, you don't want to have different computation for encouraging. So it's more like context modulated on who you're talking to or who you are with. So it's the same computation. So we ask this question to biologists: how you do internal exploration, what happens in sleep, what happens in rest, what kind of exploration and reorganization of memory occurs, so that you can be ready for new things. So all these things were asked biologists and neuroscientists to join. We have mathematicians and statisticians that we also want them to join. And the program is really going forward. Very happy with that. So I will not show you stuff from the program, which I originally intended to, but I would like to tell you about the AI Next campaign. So this is a $2 billion that DARPA put recently into research of AI for the next 5 years, and we started it just a few months ago. So if you see, we have both major programs, and we have that just started in the last few months. All those that are in boldface are of the type of lifelong learning. So they all have this kind of new types of learning, that they do some kind of learning in the lifetime of the system, and they have different tastes to that. We have another type of programs that are very fast. We call them AI explorations. And this, if you have ideas and you need money right away, we have some way to engage with you very fast. So this is what we have up to now in DARPA for AI, and it seems like we're adding all the time more. As you see, they kind of consider the first phase of AI to be the regular expert systems, and the second wave to be more machine learning, and we're going now at what they call the third wave, which is more like the learning during the lifetime of the system with all the new programs which we're starting now to have. Just to mention, in addition to software, which happens in the I2 office, we also have in the M2 office, in the microprocessor office, we have all kind of different kind of studies which are hardware, which are enabling different kinds of better AI. And I wouldn't finish without saying just one thing, that there is, I have a BAA out with a deadline of April 11, and this is called the GUARD program. And the GUARD program is dealing with adversarial, with defending against adversarial attack, which can come in many ways, in the system, in the physical world, in poisoning, in all kinds of different ways. And it has 3 different kinds of effort. The first of them is we want to fundamentally understand what causing robust generalization. So what will make our AI system more robust and less robust, what the factors are, so that we can try to introduce them in the next stages. The second one is principal defenses that are built on that, which also take ideas from biology and from the previous one. And the last one is a test bed that we're running from DARPA, but many other parts of the DoD will be joining us, where we're trying to have a really good, solid test bed for realistic threat scenarios. And here, clearly, the statisticians are more than welcome. And with that, I want to thank you.
Thank you.
That should work. Can you guys hear me? Cool. I can't believe I've run into all 3 of you guys here. It's been years. My name is Doug, and I'm a concert pianist. No, truly, Juilliard kind of thing. And if RJ is still here, I want to thank you for just throwing my hat in the ring to show up here and say something. I'm at AFOSR, and I think AFOSR has an interesting program for those who want to really do science. When I was a kid, I grew up in Area 11. That's a very special group that Henry knows. Back at Murray Hill Bell Laboratories and Homedale Bell Laboratories. So I spent 16 years growing up doing some pretty wild-ass stuff. So I really learned in my heart what I thought it meant to do research, because it was Arno Penzias who put me into Area 11. Arno was the head of research and Nobel laureate kind of guy. And so you're supposed to go out and fail. I think Pat Winston taught us that near misses are necessary in order to learn. Babies don't learn to walk by walking. They fall over a lot. That's why God made them short. That being said, you need time to think about questions. You always need to find good questions. And so, got to stay near the mic, I'm sorry. Bell Labs gave us the space as scientists back in those days to explore questions until we finally figured out the last piece of the puzzle and got it right. I think the world I live in at the Air Force, at AFOSR, Air Force Office of Scientific Research. And I didn't even know it at the time of AFOSR. I'll come back to that in a few minutes. That's where Bob Bonneau comes into the story. But our idea of doing research with any one of you is we just have an open BAA. It's just open. You have an idea? Just send it to us. Work with a program officer. There are certain ways you should work with a program officer, like tweak your idea with him or her until it reaches a really interesting fine-tuning, and then submit a proposal. But it's not a, here comes a project and you get 6 months to submit and then the project's over in 3 years and that's that. No, in physics you need short windows and runway time. I'm sorry, in computing science, I have my story backwards. Yesterday's garage in Palo Alto is, Hewlett-Packard today. Software can be out the door in another week once it works. Physics, on the other hand, has a long runway, 10 years, 15 years, 20 years. So somewhere later on after leaving Bell Labs, I went up to Watson, spent another 10 years there, working on a very interesting problem. And along came a lifelong dear friend, Dave Waltz, and Dave said, no, come work with me at Columbia at the Center for Computational Learning Systems. And unfortunately, that first year, we lost David. But I stayed on because I wanted to preserve his legacy of the center until Bonneau came along and kidnapped me over here. So I think if you're going to do research, find a place where you find a colleague where you can think about something for a significant period of time. There's no stopwatch running. It's the question. So that takes me to how do I get away from the classical piano? Somewhere along the way, I found a real meaningful friendship. And the friendship lasted for 30 years, and it's still lasting still. It still goes on to this day. I'm still in touch with my wonderful dear friend. But over those 30 years, I also did some degrees on the side. I essentially picked up some degrees. I was already at Bell Labs without the degrees, but these came along the way. So this wonderful friend and I had an argument up at MIT one day, and that's when the friendship started. His name is Marvin Minsky, and he's my teacher and my friend, and we spent 30 years going for long walks looking for good questions. So if you have a good question, not just about deep learning, but a good question, I want to hear about it. I sincerely mean that. I've built an amazing team at AFOSR. LeCun, Vapnik, Mitchell, Watson, Marvin, Josh, Tedebom, I should say. And it goes on and on. It's a really clever team, but I'm trying to do something specific with everyone's individual magical work. See, Marvin has a wonderful quote. You can't learn something well until you've learned it many different ways. That means under the hood there are many different kinds of engines. Matter of fact, this was the essence of what he talked about in his Turing Award lecture back in the 1950s. So under the hood, I've always been interested in having, as Henry might remember back in the old days when we were doing intelligent agents, many different types of reasoning, many different types of learning working together. I remember having a wonderful discussion with Vlad, Vapnik. You've got your support vector machine. This is wonderful. Can you put it together with a second type of machine? And he said, why? I said, well, maybe something magical will happen. And I remember those days with Isabel Guillon and Jan and Leon and everybody. And one day, Vlad's coming and he goes, Doug, with his wonderful Russian accent, I've got it. We're going to do it. We're going to put two things together and run an experiment. So we'll put together an SVM, and we'll put together a Minsky frame type of machine. And we got some wonderful results over whatever we do out there in the hallway. I'll be glad to talk about that. So I'm interested in, can we put things together? Now I see people putting things together. Jan's recent work is looking at putting many different things together. He's got a wonderful graduate student postdoc who's working with him on putting a memory system with a deep learning machine. Vlad just gave a talk at the Air Force out at Wright-Patterson. He was the recipient of the annual Distinguished Lecture of the Year that we picked somebody in the United States to come and talk about whatever's on his mind. Well, what's on Vlad's mind is somewhere in the future, machine learning is going to hit a brick wall and then we're going to get stuck. He means that. I believe it. I see things that Tom Mitchell's now doing in his work. He believes it. Pat Winston strongly believes it. See, what Josh is even doing with his programs out of programs that learn to learn is we're trying to come up with clever ways to put context around the learning experience. Other different pieces of information. In Vlad's teacher model from a few years back, you could call this implicit knowledge that would bias how we perceive the training data as you're running lots and lots of training data. So if we're going to be able to see many different ways to learn, thank you, then we've got to have many different ways to see the data, not just one way that we're bringing the data in with some clever vectoring. And so I'm looking for colleagues who have a really neat orange, and it does something really amazing, orange metaphor, whatever you want to call it, and they want to put it together with Tom Mitchell's Nell. Because for years, even back when I was a cyclist a long time ago with Guha and Leonard, with the psych days, why are you turning the machine off? We don't turn humans off. Humans keep learning. We met just recently because of some fellow colleagues, Henry Minsky and others. So continuous learning is fundamental. And in that machine, which we built because that's the reason I went to IBM versus to a university at that time, I wanted to have a machine explain itself to itself constantly while I was reasoning. And several of my colleagues, Leora Morgenstern, Eric Mueller, and others, would tell you that machine we called the semantic engine, some of that machine then went into the later system called Watson. It really did explain itself to itself. And when I was asked to read reviews for David Gunning for the explainable AI, I had a hard time doing that. I'm going, Saul Amaral said it the best. Saul was one of our great heroes in the field. He held the Turing chair at Rutgers. He had a wonderful quote, "Representation is everything." And to his students at Rutgers, he would say, we don't go far enough back in the literature to see we already did this. So there's things we got to be doing with explainable AI that we just start to scratch the surface. So if you have a neat idea, I want to hear about it. I want to argue about it because I love arguing. And I want to figure out how your idea fits into something that you are excited about that I could help support. But with that comes a quid pro quo. In this group, you team. You don't go sit in your silo by yourself. Even through the magic of knowing Marvin all those years, I had the chance to watch Marvin and Feynman argue in the kitchen. More questions, more questions, more questions. But even Feynman had to join a team, you know, the Manhattan Project. So I'm into building powerful teams, I'm into great questions, and I'm into really neat ideas that could be possibly linked up with Pat Winston's Genesis system, which has 40 different types of engines under the hood. So I'll stop there.
Thank you very much, Doug. So I see that we're over time and we're up against the reception, so I'm going to look at David to find out, I know that there's probably a lot of really great questions for the panelists. And first of all, let me first thank all of the panelists for a great overview of all the funding programs that they have here. Should we just take the question and answer to the reception, or how would you like to handle this, David?
Yeah, I think we should take it to the reception. Please interact with our panelists over drink.
Yes, okay. Thank you so much.
So I'm talking yours.
Juan Meza, so I'm the moderator.